All right, well, welcome back. So in this section, we're really going to start to see this kind of full power of all of this logic stuff that we were chatting about back in section 2 come full circle and actually give us a really nice toolbox for how to attack a whole bunch of different types of problems. So in this case, we're again going to be looking at this idea of we're given a whole bunch of different types of statements, and we're going to want to come up with some formal justification to actually demonstrate why that's true. So in this case, we're going to introduce kind of a whole bunch of different techniques. All of these techniques actually come back from that logic section. So you're going to see this notion of a contrapositive, as well as this idea of a biconditional, as well as negations becoming a really important tool to attack a bunch of these different types of problems. So in this case, this section becomes kind of a foundational aspect that kind of really gives us the techniques that we're going to use to start to attack a whole bunch of other things. So then when we go into topics 4 and 5, we can start to really see these concepts come together when we start attacking a few more interesting problems in this world of number theory and RSA encryption and all of those things. We're going to have this kind of formal structure under our belt so that we can actually start to attack these somewhat more interesting problems. So for now, it's a little bit of just kind of practice on how to see all of these little pieces coming together. So in this first example, we're going to be looking at this statement. And I've actually gone ahead and given this thing as theorem title because it's actually going to be something that's fairly important for us to use. So in this case, what this theorem is going to say is that if you give me some random integer, I'm going to call this thing n. I'm claiming that if n squared is odd, then n is also going to be odd. So in this case, it's actually the converse of a statement that we saw earlier in the course, this idea that we had if n was odd, then n squared is odd. So in this case, we're actually just flipping this thing around just a little bit. But the super important thing is that simply flipping these things around, that is creating this converse, is not good enough to actually keep this logical equivalence. So this is honestly a very different statement than that statement that says if n is odd, then n squared is odd. In this case, it's flipped, it's not the exact same. And that's actually where this kind of underlying delicacy of this type of problem is actually going to live. The idea in this case, and let me go ahead and say this, the idea is that if n squared happens to be odd, well, that means n squared is going to look like some 2k plus 1, which is great, whatever, that's fine. I just use this definition of being odd. What I want to do then is I want to somehow remove that square. So I'm going to go from this idea of n squared having some property down to the world of n. And in this case, I want n to look like some 2l plus 1. And I want you just to look at that just for a little bit to see why that might be a difficult thing to do. So the difficulty in this case is actually this removal of that square. Typically, when you're in an algebra class or something like that, if you try to remove a square, your gut reaction is going to be to use a square root. And that's a great technique for most things. The problem in this case, though, is that when you start introducing this notion of square roots, you might start breaking down this idea of something actually being an integer. And we know that whatever we end up at the end of the day is this L has to be an integer, otherwise this expression n being 2l plus 1 is complete garbage. If that thing is a fraction or some square root or something bad, I don't know that that's actually going to be an integer, or in this case an odd integer. So in this case, the idea, or kind of the take-home message, is that it's really hard to remove squares. It's easy to add squares. You just take some expression and square both sides, and then you do a whole bunch of operations. And we know this idea of this closure works really nice with kind of multiplication and squaring and things like that. I'm not losing any of these fundamental properties. But in this case, the square root actually does remove that. So what we want to do is we want to somehow go the other way. Well, we know that we can't just do this converse because that's not logically equivalent. But what I can do, if you kind of go back kind of in the back of your brain and remember some of this logic stuff, is that we do have this ability to flip these things as long as we add negations to everything. That is this idea of this contrapositive. So in this case, the idea is that if I have this statement that currently looks like A implies B, this is going to be logically equivalent to the statement that says not B implies not A. So that's the form that I want to see this thing take. So right now it says n squared is odd implies n is odd. Well, the contrapositive of this thing is then going to read something of the form if n is not odd. So in this case, if n is even, I'm going to go ahead and write that. So if n is even, well, what's going to happen? Then I'm going to have this negation of my initial hypothesis. And right now it's saying n squared is odd. So the negation of that would say n squared is not odd. Or in this case, it's going to say n squared is even. So in this case, my contrapositive of my thing is going to say if n is even, then n squared is even. And that is, hopefully you can believe, something that is much easier to actually show. This is actually a pretty easy statement to look at. What's going to happen is that if you start with something being even, so in this case n is going to look like a 2k, Well, what's going to happen is that when you try to square this thing, you're not going to break anything in terms of this integer stuff. So right now it's going to say n equals 2k, and this k is going to be some random integer. Well, when I square everything, so I'm going to take this 2k, and I'm going to square this expression, which turns into a 4k squared. I can break a 2 off of that thing to turn into a 2k squared. So now you see this 2 multiplied by something, and that thing is most certainly going to live in this set of integers. I have this k, which was an integer. Squaring it keeps it as an integer, and then multiplying it by 2 is again going to keep this thing as an integer. So in this case, I can see that this boxed expression is actually going to be a true statement. And this statement in a box is going to be logically equivalent to my original statement that I started with. So since I can prove the thing in the box, it's going to say that the original thing is actually true. So when we come to actually trying to write this thing up, what's going to happen is that you have to let the reader know that you're doing something a little bit funky. Typically, when we're kind of just diving into one of these proofs, we're going to assume that you're going to have whatever the hypothesis is going to be your initial assumption. And then after that, you do a whole bunch of work to kind of hopefully see that final conclusion. That type of proof is referred to as a direct proof. You're giving me this thing that looks like A implies B. Well, I better see this assumption on A occurring at some point in time, and then a little bit of math magic occurring in the middle, and then ultimately getting towards your conclusion. In this case, because I'm doing this little switcheroo, I'm actually introducing this notion of this contrapositive, I better let the reader know right away that I'm doing something a little bit weird. Formally, this idea of kind of using this contrapositive is what's referred to as using an indirect proof. So in this case, it's a little bit weird. It's a spin on the kind of classic if-then idea. So in this case, all you have to do is just tell the reader that you're going to be using the contrapositive, and just to kind of make sure that they know what the contrapositive is, it doesn't hurt to actually say what the contrapositive is. So in this case, I'm going to say something along the form of, we will prove this result by proving the contrapositive. So in this case, I'm letting them know, hey, the contrapositive's on its way. Then in this case, I'm actually just going to tell them what the contrapositive is. So in this case, that is, I'm going to show you that if n is even, then n squared is even. And you have to believe me that those two things are in fact these contrapositives of one another. So in this case, the original thing is logically equivalent to this new thing. So then it basically turns into a brand new little proof. So now I'm going to make this kind of statement of, well, now I'm going to have this even thing. So since n is even, I know that there's going to be some integer k such that n equals 2k, and then it's just going to go into that whole algebraic step. So I'm going to square this n, I'm going to do all of that little rigmarole that I just did kind of back on my scratch paper, ultimately going towards this idea that it's going to look like 2 times some random integer, and we know that that's going to actually introduce this notion of being even. So in this case, since 2k squared is actually an integer, it's going to follow that this original thing, this n squared, is in fact an even integer. So in this case, this idea of proving the contrapositive gives me my original result, which is a really slick trick. So that contrapositive actually becomes a very, very powerful thing. A lot of times, if your original hypothesis is challenging to work with, but your conclusion is not so bad to work with, this contrapositive is going to allow you to flip those things around as long as you put negations on things and then work as kind of however you want to from there. So I like the contrapositive. It is a very, very nice little trick. It saves you a lot of time and kind of a lot of pain when it comes to actually attacking some of these other statements. So now I just wanted to take one extra little minute or so to chat about really what's going on with this result. There's a lot of special properties going on. In this case, what's happening is that if you remember from way back in the beginning, and I alluded to this in the beginning of this video as well, that we actually did see half of this result already. Earlier in the course, we actually had this statement that said, if n is odd, then I'm going to have that n squared is odd. So that was this original result that we looked at way back when we were first starting to chat about how to actually formulate some of these proofs. Well, now we're just going to show, or now we just did show, this idea that if n squared is odd, then I'm going to have n is odd. So in this case, I actually have both the forward and reverse direction of this statement holding true. So the idea is that the original hypothesis says that if n is odd, then n squared is odd. But what ends up happening is that the reverse direction actually holds true. So in this case, it is one of those really weird cases that the original statement and the contrapositive both are true. It doesn't have to be. And that's the big caveat always, is that these statements don't always work as a two-way street. But in this case, it actually does. So what I can do is that I can actually make this a slightly more impressive theorem. What I can do is I can still have this idea of you give me some random integer. So in this case, for any integer you'd ever want to give me, I'm going to replace this if-then structure with this fancy if and only if statement. which is this biconditional statement. So this is going to have this notion of it's going to work in the forward direction and it's going to work in the reverse direction. It's this idea that I have this nice double-headed arrow. So that's the really kind of neat thing that's actually occurring in this case. So if you go back to actually the kind of logic world, this makes sense. We have this idea of what this biconditional is all about. This idea is A if and only if B is actually logically equivalent to this statement that says A implies B and B implies A. And that actually gives us a little bit of insight on how we're actually going to show one of these things. And what ends up happening is that if you actually want to prove or kind of formulate this kind of nice argument a little bit cleaner, is you're actually going to break this thing into two smaller little proofs. What's going to happen is that you're going to prove what's referred to as the forward direction. That is this kind of original implication arrow. So in this case, you're going to prove if n is odd, then n squared is odd. And that one we already know how to do. And then you're going to have a second version of that proof, which is going to be proving the reverse direction. So in this case, you're going to make this assumption that says n squared is odd, then gives me that n is odd, which is actually the result that I just got done showing. So in this case, you combine both of those things together, and you get this nice proof of what's referred to as this biconditional, this idea of this if and only if is going on. So it is kind of sometimes scary to see this big thing going on, and the proofs look really long, but if you look at the proof as actually two separate little proofs, it becomes a really easy thing to see. So in this case, I'm actually just going to sketch what the big argument's going to look like. So just like that previous kind of idea, what's going to happen in this world is you want to go ahead and right away tell the reader or whoever's looking at this thing that you're doing something a little bit funky. In this case, I'm going to let them know right away that there is a biconditional statement going on. So in this case, there was that if and only if thing right away, and I can see that that thing is going to somehow influence my actual proof. So in this case, I'm going to say we're going to prove this biconditional statement by doing the two separate little conditional statements. So in this case, I'm going to have my forward direction, this A implies B, and then I'm going to do the reverse direction, which in this case is going to be the B implies A. And then that's exactly what I'm going to say. I'm going to do the following two conditional statements. The first one is for the forward direction, so if n is odd, then n squared is odd. And then I'm also going to do the reverse direction, which is the backwards arrow, which says if n squared is odd, then n is odd. And then it turns into two little proofs, and I like to indicate which direction I'm going with by simply saying for the forward direction. If I'm actually doing it on kind of pencil and paper, I'll actually just sometimes do this little forward arrow with little quotes around it saying like, okay, I'm doing the forward direction. So in this case, for the forward direction, I'm going to assume that n is going to be an odd integer. And then I'm just going to basically copy and paste that proof that I had from earlier in the course, which is one of the nice things about typing these things is that you can save yourself a little bit of time because you just copy and paste things and all of a sudden it's done in this case. So in this case, I'm going to assume n is an odd integer, and then here's where this classic proof of if odd, then square is also odd. So in this case, since n is odd, there's going to exist some other integer k such that n is going to look like a 2k plus 1. You go ahead and square that thing. You're going to do this classic trick of taking 2k plus 1, squaring it out. You're going to see this 4k squared plus 4k plus 1. Rip a 2 out of that thing, and you're going to now see a 2 multiplied by some random integer plus this little remainder of 1 in this case. Because I have this particular structure, what's going to happen is that this overall n squared is in fact going to be odd. For the reverse direction, this is actually the proof that we just got done doing. I'm going to say for the reverse direction, and now I'm going to trigger into the fact that I'm going to use the contrapositive. So it's kind of two rabbit holes that I've gone down in this case. I started with this giant biconditional expression. I then ripped this thing into two little bits. The first bit was this classic n being odd implies n squared is odd, and then the reverse direction was this weird kind of mix-up one that I actually had to flip the argument around using the contrapositive. So I'm again going to let the reader know that, hey, their contrapositive has in fact been used. I'm going to tell you what the contrapositive is, and then I copy and paste that argument that I just got done showing, this idea that if you start with an even and you square that even, it's going to stay even, therefore proving that this contrapositive is actually true. So in this case, I apologize that this video got a little long. I just wanted to do all of those two things at once just because it's nice to see just the original contrapositive and then this conditional one come right afterwards, because really what's going on in that case is that it's the same argument kind of taking shape. And it's kind of nice to see the two little things back and forth a little bit, and we'll see a whole bunch of other examples of these types of things as well. So don't be kind of scared by the size of some of these things because they do become a little bit lengthy. You really just want to look through these things with a fine-tooth comb to see kind of what the internal guts are actually doing. And in this case, the guts aren't actually that bad. It's a little bit of symbol pushing, and it's a little bit of writing, but if you've typed some of these things out already, then it's nice and you just copy and paste them and save yourself a little bit of work.